everyone, welcome back. So let's give a little recap of last lecture. So we arrived at Einstein field equations, where we introduced, for generality, a cosmological constant. And we need to introduce such a term to explain the accelerated expansion of the universe. On the other side, we have the source term, which is our beloved energy momentum tensor. Then we have seen that we can carry this term on the other side and obtain an energy momentum tensor that is the one associated to the cosmological constant. Let's call it lambda. Okay? This is not an index. That's just to say that is the energy momentum tensor of the energy of the cosmology associated to the cosmological constant. And we basically made a construction such that we are treating this term as an effective fluid. An effective fluid that has its own pressure. It has its own density. So let's say the pressure of the cosmological constant, the pressure, again, of the cosmological constant, with an equation of state, and that's a key point, which is equal to -1. Okay? So in cosmology, when we are trying to understand if the universe actually contains this term or something more complex, for example, a scalar field, dark energy, that we are going to study in next lectures, we investigate departures from this term. Okay? So we look, our universe has a term that have a behavior of this sort. Yes? That's a cosmological constant-like term. Is not? Then it must be a dynamical field, as we are going to see. This would be dark energy. Okay? So this is a key point. Then we used basically a basic concept of thermodynamics, the first law of thermodynamics, and we derived I gave you the expression for the adiabatic condition. But it's reasonable that the universe obey the first law of thermodynamics. Because the universe, as a definition, is everything, and by definition is therefore a closed system. Therefore, it's not going to lose energy. It's not going to our energy to flow, I don't know, in another universe or we don't know where. Okay, so it's a closed system, and it obeys the first law of thermodynamics. Knowing that, we used this law to get a constraint and actually to understand what is the evolution of the density of the various fluids that can enter in this term with this simple expression, where again you see the importance of the equation of state parameter of the fluid that we are talking about. And since the fluids that we are going to discuss, which are the radiation or relativistic terms, the matter terms such as baryons, dark matter, and the cosmological constant with that index, we treat them as completely decoupled, so there are no coupling between these two terms, meaning dark energy is not affecting the relativistic or the matter term and the relativistic term directly, only through gravity, because this has an impact on the overall dynamic of the universe. Okay, but there is not a direct interaction, and therefore we can treat them separately, and we identified 3 dominant epochs, right? Because we found out that radiation has a log density like that against log A, and now you know what A is the expansion factor of the universe that we have seen in the Friedmann, Lemaitre, Robinson, Walker metric. That is a function of time. So you can use A or T, or as we are going to see today, redshift as time variable. Okay? The universe expands as a function of A, you can say, or as a function of redshift. Right. So relativistic component has a steep density drop, proportional to a to the power of -4. Matter, goes directly proportional of A to the minus of 3, and the cosmological constant is constant. Okay? As it's clear, minus 1, 1 minus 1, that's 0. There is just a constant dependency. And therefore, we can identify a radiation-dominated, a matter-dominated, and in the future, dark energy or cosmological constant-dominated universe. And we are sitting here, okay? Where roughly the energy density of matter and of the cosmological constant are about the same, okay? 30% roughly of matter, including baryons, dark matter, and all, and 70% roughly of dark matter. Then, what have we started to look at? After we characterized the energy momentum tensor and sort of got rid of the cosmological constant just because we let it absorb by the energy momentum tensor, we went to investigate this other term, geometry. Geometry, where we had to define the symmetry of our system, homogeneity and isotropy. That's because Einstein field equations are a mess, and before starting to touch them, you impose all possible symmetries that you have. And luckily, our universe is a simple object, and we have all possible symmetries that we can impose to this object, which is homogeneity and isotropy. That's the cosmological principle in one word. Okay, these are the symmetries that we impose to the metric G mu nu. And as we have seen, we set G00 component equal to -1. This is a way of setting the clock ticking of a free-falling observer that we call fundamental observer, as we have seen. Then we have the GE0 and the GIJ terms that are both equal to 0 to respect isotropy. Because otherwise, if these terms would be different than 0, we would have a privileged direction breaking one of the assumptions within the cosmological principle, and we don't want that. Then what we did was to introduce a dynamical expansion in which, if we have just in which Gij, so only the spatial component of our metric, we want them to scale isotropically. Therefore, we introduced a scale factor, A, that depends on time. So that's the dynamical, the free variable in our system. That basically inflates or deflates, it depends on the universe that we are considering. In our case, is expanding, so it inflates the metric associated solely to the three spatial components, 1, 2, and 3. Okay? That's what we did. Another thing that we did, so we have this isotropic expansion, but then within the metric of spatial components, we introduced a constraint on the curvature, right? We realized the fact that the curvature of the universe that we can represent with with the Ricci scalar, okay? That's a measure of the curvature of the universe, as its units are 1 over meter to the power of 2, so it's the inverse of a length squared. And I showed you that basically R is directly proportional to the contraction of the Einstein tensor, so all of the term which is left on the geometric side. And we wanted this guy to be, so that the G, E, J components, we wanted them to be, the G, E, E component, so that's the contraction, so that's G equal to that, so G, E, E, repeated index, only special component, we want it to be fixed, a constant. Namely, given a time slice, we want the geometry to be the same all over the places, homogeneity. The geometry here is the same there and all over the places at a fixed time. Geometry can evolve as a function of time, but given a time slice is fixed, curved, flat, or hyperbolic. Okay? Having done that, we identify the metric. We build up the metric satisfying all these conditions, which is the Friedmann, Lemaitre, Robertson, and Walker metric that we wrote in this way. So we have minus c squared dt squared plus a squared t. So this incorporates the dynamical expansion. That's the first term for the synchronization, so for the unit of the clocks. And then we have the three-dimensional components that you can, contribution of the three-dimensional components that you can write in Cartesian coordinates, x, y, z, or in spherical coordinates as we did in the lectures. Okay, you're free to choose whatever you want here. And you use the one that is convenient for the task at hand. Nice. So we have a function that is proportional to the r plus r squared, the omega squared. And a thing that I stressed is the fact that how you measure the distances along a radius is given by this function times dr. Okay, that's the interval, the d interval along the radius. And you have that surfaces or angles on the surfaces, or surfaces that you measure through angles, scale in a different way with respect to this one. Okay, so you have a distinction between the r, the distance that you go along the radius, and the distance that you, or the radius that you use to measure surfaces on, areas on surfaces. Okay? And look, we had this term, which is called curvature. Okay? It's just a parameter, and this is fixed. It doesn't have to be confused with the real curvature of space-time, like as given by the contraction of the Ricci tensor, so the Ricci scalar. Curvature parameter. And you realize the fact that if k is equal to 0, what happens? This disappears. What's that? This is a standard. If you look only at this term, you see it is the trivial interval in Cartesian, in Euclidean space, flat geometry, right? K equal to 0, this disappears, the r squared plus r squared, and you see that the meaning of separation along the radius and the radius that you use to measure areas on surfaces is the same, has the same meaning, okay? They scale in the same way. Euclidean. Now let's give a look about this term, because we can simplify our life just by renormalizing scales such that this guy is always equal to 1, 0, or minus 1. Let's do that. So k is indeed a real number in general, but what we do, and so therefore you can have k smaller than 0, k equal to 0, or k larger than 0. But then we apply sort of a trick, because we can go k, we redefine it as k over its own modulus. So it can be only 0, 1, or minus 1. And this works only if we rescale the radius as the square root of the modulus of k times r. Why does it work? Look here, for example. So k, we divided by the modulus of k, and r squared we multiply by the square root of modulus k, which is modulus of k that cancel with the factor that we introduced here. So you see, I introduced a square root of k, and I multiply by a square root of k. So I haven't done anything, but I changed the definition of my k. And the same goes for this factor, because this factor is going to rescale this dr and this r to the power of 2, right? Therefore, not to mess up everything, I need to rescale this guy as well. Okay. After we have done that, we achieved the result of expressing k as 1, or let's start with 0, so that's a flat geometry, Then we have 1, which is a spherical geometry, or closed, they give us a closed universe, or -1, which is an open. Oh, and let's go, let's keep it hyperbolic. Hyperbolic, or open universe. That's what we can have, okay? About this name, the flat I already explained, that's trivial. Spherical and hyperbolic, I'm going to show you why we call them like that and why this corresponds to a closed or an open universe. So let's give a look at the case k equal to 1. We introduced, we make a change of variable, okay? And the change of variable that we are going to do is to introduce, to substitute the radial scaling with this psi, and we write it like that. So the interval now, right, the power of 2 of the interval along this new direction is given by the r squared over 1 minus r squared. You see? We basically, what we did is to call this guy d of xi to the power of 2. All of that, see? All of that is this. We made this change of variable. And now, keep in mind that k here, you see, is 1 because of the rescaling that I did earlier. And now you see why we did this renormalization, because now we can easily integrate this guy. So it makes our life simpler, this rescaling of the curvature parameter. And by performing the integral, we just have a direct relationship between r and xi, just a sinus. That's why, you see, that's why the universe, this geometry, is called spherical, because it refers to sinuses and cosinuses. Okay, in this case are sinuses. Spherical. Nice. Then let's give a look at the properties of this guy, and let's take xi equal to 0. To what does it correspond to? Well, it corresponds to an r equal to 0. It's just the sinus of 0 is 0. Then let's give a look for xi equal to pi half. What is it equal to? Pi half is up here, therefore the sinus is equal to, therefore the radius is equal to r equal to 1. Sinus of pi half, 1. Then what we have, if xi is equal to pi, what we have, r equal to 0. So we start with 0, 1, 0. You see, we have sort of periodic condition. In fact, we see that looking at that, we realize the fact that r actually is bound between 0 and 1. You cannot go r to infinity. It's periodic. Okay, so the absolute value of r is bound between these two values. If we now give a look at the volume that we can compute just by computing the three-dimensional interval, so this is a 3D volume, so only spatial. It's just evaluated through the metric, only the three-dimensional metric component, so let's label it with this 3 to make it clear, and the x3, so where x is x1, 2, and 3, okay? We plug in now what we know about the metric of the Friedmann, the metric, and Robinson, and Walker, so we just plug in all the spatial component of the metric, and by performing the integral, we realized that this is equal to 2 pi to the power of 2. The volume of the universe is finite. Nice. Let's continue. And let's give a look at the last case. K equal to -1. So again, we have a parameterization that now is going to be slightly different, because instead of this 1 minus r to the power of 2, if k is equal to -1, we are going to have the r squared divided 1 plus r to the power of 2. Which means, let me write it here to be super clear, the r to the power of 2 divided 1 plus r to the power of 2. And then we do the same game. We do the same game, but now we look for c equal to 0, r indeed goes to 0. Sorry, I have to integrate first. So let's make the integral, and we get, to get the direct relationship between c and r, and in this case, we have a sinus hyperbolicus. We have an hyperbolicus sine. That's why this is not called spherical, but is going to be our hyperbolic geometry. Now you don't need to I don't need to convince you. You realize the fact that in this case, if we are not anymore sinus, but the hyperbolic sinus, just by the properties of this function, we realize the fact that r can go between 0 and infinite. That's why we say that the universe is open. Okay? Nice. With all of this construction and having now the understanding of the meaning of this open, close, spherical, hyperbolic, and flat geometry, and having reshuffled slightly our Friedmann, Lemaitre, Robinson, Walker metric such that k is equal to 0, 1, or -1, we can, again, reshuffle this metric even further. I'm showing you this other way of writing it because you find them in the literature, okay? So if you see the Lemaitre, this metric written in various fashion, you kind of know why and where they're coming from, okay? Anyway, another way of writing, I've introduced this xi, this xi new variable. We can now also write the metric like -c squared d t squared. We never worked on this side, so it remains untouched, plus a to the power of 2, that is dynamically changed as a function of time. Then we have our dxc to the power of 2, regardless of the choice that we have done. I have two definitions. If you want 3, because then we have also that the dxc square is equal to the r to the power of 2 for a flat geometry. And again, this comes from the fact that k is equal to 0 up there. And to be general, you can write it as this function that is changing. It's basically the function that rescales, relates xi to the radius. And then we have the theta square plus sinus theta, the phi, the power of 2, once I introduce explicitly the omega, okay? So the angular components of the spatial terms, okay? And our function, fk of xi, are just the one that I wrote earlier. So are going to be xi is equal to r for k equal to 0, xi, f of k is sinus of xi, and then we have sinus hyperbolicus of xi. So k equal to 1, and k equal to -1. and yet another way of writing the metric. Okay? That one is just a very trivial step, but is very important. Okay? Let's write the s to the power of 2, our minus c squared d to the power of 2, plus a to the power of 2, or all the special contributions. Okay? You can write it again, this term in spherical coordinates, as we did. So you would have all of that into here, or in Cartesian coordinates, the x to the power of 2, the y to the power of 2, the z to the power of 2. Okay? Now what we can do is to group this guy, this a, in front of everything. If we do that, we basically obtain a to the power of 2, and then we have minus a to the power of 2, the t over a to the power of 2, 2, plus the other components. Let's write it in Cartesian so that you also have the expression written in another, with another set of coordinates. You have it. And now look at this guy. The t over a, we can call it the tau. So it is the t over a, all of it to the power of 2. We can call it the tau, and of course, to the power of 2. We call this time tau, conformal time. And the example that I've chosen here, how does it look like, this guy? Which geometry do you find there? Which geometry do you see? Which geometry do you see? Minkowski. Exactly. This is a flat geometry. It's an example. I didn't write down the whole FK term and everything. This is just a flat geometry. Okay? Of course, you can do it also with an hyperbolic. So these terms could represent an hyperbolic geometry or a spherical geometry. This is just an example, okay? Just to show the concept that we want to highlight, which is this one, the conformal time. Now look at this expression. The only difference with respect to the standard Minkowski time is this guy here. Okay? So this object is conformally flat. You have a conformal transformation of your metric. Yeah?
One question about the way you introduce this auxiliary function f. For dimensional reasons, shouldn't it be an f squared? Like we recover r squared?
Oh, sorry. Okay? So these are the expressions that I wrote up there. Okay. Now let's see. Yes, because then it goes the Dixie. Fk of psi. Okay. Good. Now that you've seen these various ways of reshuffling the metric and having it expressed in different ways, what we do, we need to solve or to get an explicit expression for Einstein field equations in our universe once we impose our symmetries. Okay? So we do that. We plug G into Einstein field equations. So we want to plug it into G mu nu, for which we need what? We need the Riemann, the Ricci scalar, the Ricci tensor and the Ricci scalar. Therefore, we need to evaluate explicit the Ricci tensor that we can use to compute the Ricci scalar. But for all of that, we need to compute the Riemann tensor. For which we need what? we need the Christoffel symbols. So the usual GR stuff is to start by computing the Christoffel symbol. You compute the Einstein, the Riemann tensor. Let's go in order. We compute the contraction of this guy that gives you the Ricci tensor, the contraction that gives you the Riemann, the Ricci scalar, and then out of it you can compute G mu nu, the Einstein tensor, that allows you to write all those equations in an explicit form. Okay? After we plug it in, I just give you a few examples of the term, because these are just, in the end, algebraic expressions with not much physics involved. You find all the solutions in the script. Just give you an example to give you a flavor of it. For example, the G011 term is equal to A dot over 1 minus k to the power of 2 times C. For example, then you have the Christoffel symbol 0 to 2, which is equal to 1 A dot over C R to the power of 2, and then you have the others, okay? So expressions of this sort. You see, the only variable is A, and that's the case for all the other components, all the other Christoffel symbols, okay? And you don't need to compute 0, 1, 2, 3, 4, 1, 2, 3, 4, etc., all with all the permutations, because there is a lot of redundancy between the terms. So you have many that are always the same. For example, just give you a pile of them that are identical. 1, 3, which is equal to this one, 2, 1, which is equal to 3, 3, 1, and they're all equal to 1 over R. This is obvious, right? You see, the Christoffel symbols, by construction, within general relativity, are symmetric with respect to the lower indices. Therefore, the 1, 2 is equal to the 1, the 3, 1 is equal to 1, 3, etc., etc. All of that. Once we have that, we just do this cascade of computations. I cut it short, and again, I show you just a few of them, at least only one of them. So Christoffel symbol, then you have your Ricci tensor. For example, the 0, 0 looks like that, 3a dot dot over a c to the power of 2. And the only other one that are non-trivial are R11, R22, and R33. These are the three non-trivial values for the Riemann tensor. Then you can contract the guy, and what you obtain is the Ricci scalar, which reads 6 over a to the power of 2, a dot dot over c to the power of 2, plus a dot to the power of 2, c to the power of 2, plus k. So you see the curvature is popping up. Is there in your evaluations, right? You can find it here, and you can find it also in the Christoffel symbols. Let me give you one where you can see that. For example, in this Christoffel symbol 1, 1, 1, you have minus k r over 1 minus k r to the power of 2. Okay? So you see we have k as a fixed parameter given the cosmology that we have at tens. So it's a fixed number that you give. And then we have a, which is the dynamical variable of our system. The universe, our system, is evolving because of a. A is evolving as a function of time. Okay? All right. Now that we have all of that, we can basically plug in our expression, because we have the Ricci tensor, the Ricci scalar, and with that, we build our G mu nu. We have our G mu nu, which is equal to R mu nu minus 1/2 R G mu nu. We plug it in, and we have our Einstein field equations with an explicit metric and all the symmetries that we want imposed to our system. Now you can say, ooh, we have 4 times 4, 16 equations. No, well, there are intrinsic symmetries of the mathematical construction of G mu nu, therefore we have less components. Plus, we have also all the restrictions that we imposed in our system, meaning homogeneity and isotropy. Look at the metric. Let's give a look at that one. Look at the metric. How many terms are equal to 0? All the off-diagonal ones. This kills a lot of terms in G mu nu. Many are going to be just 0. Others are going to be just repetitions. In the end, what we obtain after we have done this substitution, we obtain only 2 equations. Oof, that's good. Okay, that's a relief. So when we set mu nu equal to 0, 0, so time components, our equations, Einstein field equations, boil down to that. And the other one is mu nu equal to E. So the 1, 1, 2, 2, 3, 3. Okay? And guess what? They are all the same because homogeneity and isotropy, right? 3 directions. The properties of space-time must be the same. And this is just popping up as a natural consequence. Okay, and in this case, we get A dot dot over A c squared plus 2 A dot over AC, all of it to the power of 2, plus 2k over over A to the power of 2 equal to 4 pi G over C to the power of 2 rho minus P over C to the power of 2. These 2 equations are called the Friedmann equations. Once you impose the symmetries, you have your general structure of general relativity given by the Einstein field equations, and the solutions are called the Friedmann equations. So this is the equation 1, that's the equation of 2, and you just find them written in this way. So here I'm just dividing by these 2 guys, so these just drop away. Minus 4 pi G over 3, rho plus 3P. Yes, 3P over C to the power of 2. And the other one, the equation number 2 is, let me write it here, is h to the power of 2. Now I tell you what h is. 8pg over 3 rho minus k a to the power of 2. Okay? And h is just a definition. And it's called the Hubble function. A dot over A. Nice. So you see, in the end, we have 2 equations that give us the acceleration of A and the first derivative of A. Now again, for completeness, what we can do is to specify here our fluids, because rho looks like only one fluid, right? But remember that there are all the species that belong to the universe. They are all there. Therefore, we can write them in an explicit form, because we are going to have the density of matter, the density of the radiation, and the density of the cosmological constant that are entering here. So we can write them in an explicit form. So we are going to have our constant, A pi g over 3. And then we have rho of matter. With that I mean baryons and dark matter, plus the one of radiation. And then I would have plus rho of the cosmological constant. But now I keep it separate just to split the term for visual impression between, let's say, normal stuff in the sense of matter and radiation and the cosmological term. Okay, so I will keep it outside. So our rho will be multiplied by that. Minus k over a to the power of 2. Oh, well, sorry. Here we only go, we only already kept the omega, the k separate. Yes, exactly. Plus, what would be here? What I just said. Plus rho of the cosmological constant multiplied by this guy. And this gives us our cosmological constant value over 3. Okay? Rho matter plus rho radiation plus rho cosmological constant. And we can do that, so we can just sum them up in this way because we treat them, as I already said, as independent. They are not interacting, not interacting. Okay? They evolve independently. Therefore, what you see is that the universe behaves with an effective fluid, which density is the sum of all of those. Last bit of manipulation of the equations. Having everything written in this way, we can give a look, define additional quantities that are extremely relevant for the understanding of the universe as a background term. So it is a homogeneous and isotropic structure that we are imposed to our equations, among which we have the critical density and the energy density contrast that is typically used in cosmology. These big omegas that you might have seen in a lot of plots where the cosmological constraints pops up. Okay? So let's see whom they are. So let's start with the Friedmann equation number 2. And here what we can do is to impose k equal to 0. What happens? The k disappear, and we can isolate rho c that we define as 3h to the power of 2 over 8 pi g. That's the critical, that's the critical density. Okay, I worked there. Here, okay? I set k equal to 0. You see, k equal to 0. And then I isolated rho. And we get this expression. This is the density for which the universe is flat. Okay? So that's the rho for which k is equal to 0, is flat, okay? Then what we can do? We can work again on the Friedmann equation number 2, but now what we do, we divide it by h to the power of 2. So what have I done? I divided this expression, both sides by h to the power of 2. So here we will get a 1, and here we will get the ratio of this side. Therefore, we have where are we? Yeah. 1 equal to 8 pi g 3h to the power of 2 rho minus k c to the power of 2 a to the power of 2 and the h to the power of 2. So you see, I just brought the h to the power of 2 on the other side of the expression, and now we call this guy omega, and we call this guy omega k. What are they? Omega, by definition, if you now look at this expression and the value of the critical density, you can see 8 pi g divided 3 over and 3 h to the power of 2. So you see this guy is actually rho critical to the power of -1. So we have a rho divided the critical density. Rho divided rho critical. We call it the density contrast. And this omega is just a definition. So we call it this omega that we are associating now to the curvature. We call it with the minus, that's why there is a plus here, is k c to the power of 2 divided a to the power of 2 h to the power of 2. I just called this guy omega k. Of course, this guy must have the same unit of this one, right? Therefore, is a density contrast as well. Define this way. This is the density contrast of curvature. Now that I have this expression, you see I have 1 plus omega k. Look at that. 1 omega k. What can you understand? What do you understand from this expression? What happens if k is equal to 0? These terms disappear. This one is not here anymore. What's this condition, k equal to 0? A flat geometry, a flat universe. So if you impose k equal to 0, this term disappears. So let's just keep our eyes on these two sides of the equation. Disappears. Therefore, we have that omega is equal to 1. So if the components of the energy density, the contribution to the energy, the total density contrast of the universe is equal to 1, the universe is flat. And, by no surprise, is exactly the definition of the critical density, because omega is the ratio of rho over rho c, and therefore, if the density of the universe is equal to the critical density, this guy is equal to 1. Omega equal to 1 corresponds, is the other way of seeing if the energy density of, is another way of saying that the geometry of our universe is flat. Okay? So let's go through all of that, and then I clean the board. Okay. So this was just the recap, where I'm not going to repeat. We started today from the Friedmann-Lemaitre and Robinson-Walker metric. We renormalized the curvature that is a floating number, so it's just a real number, not an integer number. But what we did is to make the trick of renormalize it with respect to its own modulus, such that k can only be 0, 1, or -1. And by doing that, one has to take care not to screw up the metric by just placing values of the square root of k such that the metric is not affected. It's just a rescaling on length scale, nothing more than that. Having done that, we then started to look a little bit into the properties of this metric by introducing this auxiliary variable, key, and we basically recalled all this term here, rewrote all this term here as d of k to the power of 2, with k equal to 1 and with k equal to minus 1, such that we can easily obtain a directly and simple relationship between R and K. So just by integrating this guy, we obtain this expression and this expression. Then we investigated further what's the meaning of all of that, and we realized the fact just by looking at varying the values of K, we look at R, and we realize that the values for a spherical geometry, spherical because we have a sinus here, is bound between 0 and 1. Then we looked into the volume of our universe just by computing the universe, keeping in mind of the metric that we are considering, where the k is inside there implicitly with the k equal to 1. We realize the fact that this is a finite number. The universe has a finite volume. It's closed, okay? It has a closed surface. Then we have k equal to minus 1. And again, the relationship leads us to that. This is just the sinus hyperbolicus, which is not bound, and therefore R is going between 0 and infinite is open, okay? Having done that, we played further with the metric. And we just rewrite it by having done basically anything, but writing this term, so that modification up there with an f. And as a function f, which is generic. Then I introduced another concept, which is rather important, which is the one of conformal time. And we achieved that just by grouping A, that appears only in front of the space component of the metric, in front of everything, okay? So if we do that, you understand that here we can have the three types of geometry, flat, with k equal to 1, hyperbolic, or spherical. Here, for simplicity, I just wrote down the flat one, that we can also write or in spherical coordinate, as we did up there, or in just Cartesian coordinate, the x, y, and z. And you realize the fact that if we do that, this is exactly the and we introduce this, this new way of calling the time, the t over a, calling conformal time. What we have here is an expression which is the Minkowski metric. Okay, the universe is conformally flat. The geometry is flat, it's just expanding, is stretched as a function of time. So what's happening here? It happens that the tau is changing as the universe is expanding because of this guy. Okay, so the time rate, the tau, at which the time is flowing, is changing because of that. Okay, once we introduce this, the tau. Oh, what are you doing there? Yeah. Okay. So you see, I brought the a outside, so these two have to cancel. There should be the c squared. So I wanted to see probably write a squared, and I wrote c squared. The way around. Okay. Okay, so that's completely Minkowski. And you see that when we do that, and we introduce this tau, as the universe is expanding, it's like that the time rate is changing. This is just a matter of defining the flow of time. Okay, it's just a mathematical construction. And also, we can do it in this room. Okay, I can define the tau, the time of your time divided a function that I can invent. Okay, but it's always the time. It doesn't change its physical meaning. It's just rescaled in a different way. That's very convenient if you for computations and for deriving further properties. Nice. With the metric, what we said, we plug it into the Christoffel symbol to derive the Ricci tensor that we contract to get the Riemann tensor that we contract to Ricci tensor, and then we can combine together to obtain, you see Ricci Ricci plus the Ricci tensor plus the Ricci scalar, we combine them together to get the Einstein tensor, and boom, we have our full expression for the Einstein field theories. Then, in the end, boils down just to two independent equations. Okay? These are two independent equations, slightly smaller reshuffling, that are typically written in this way. So this is a key result in which we have the Friedmann equation number 1, where we have an explicit expression of double derivatives with respect to time of the expansion function. And then we have this other expression in which we have acceleration of A, so the time derivative of A, and this H is called the Hubble function. Okay, you are going to see this expression popping up all over the places because it incorporates the dynamic of our universe. Okay. Moreover, what we can notice, are these two equations independent? No, they are not, because we have this other equation which is still valid, the adiabatic condition. Okay? And through the adiabatic condition, you can relate one with the other. They're linked. Not independent. And that's because we are using the adiabatic condition. Or if you wish, you can look into that the way around. You can combine these two equations, and you are extracting the adiabatic conditions. Okay? So you can think that those equations are implying the fact that the universe is a closed system. Okay, nice. So we can have a break as I wipe up the board. I'm going to give you a few other expressions that are useful, and another way of writing this Hubble function, which is the one that is typically used, because, as I said, they are independent. The one that is used the most is this one. Okay? And since we introduced these new variables, that, by the way, I forgot to mention now in our recap, since we introduced the critical density and these omegas, you see, we can just divide this guy and multiply to the critical density to have this expression in form of sums of omegas. Okay? Get much more compact, and these are all the values that are typically shown in the literature. Okay? So this is going to be in a few minutes. So we can resume at 15:30.